Hello, and welcome to today's on Semiconductor Technology webinar. Our topic today is improving solar inverter efficiency and power density with SiC hybrid and SiC MOSFET modules. I'm Chris Kosserswit on Semiconductor, and I'll be your moderator today. At the end of the webinar, we will be holding a Q&A session to answer any questions you may have. During the webinar, please open the Q&A window on the right side of your screen and send your questions to all panelists. This webinar will be recorded and posted at onsemi.com. You'll be notified via email when the webinar is available. Now let's meet today's presenter. John Harper works in the Power Solutions Group at ON Semiconductor, where he is a product manager for power modules, IGBTs, and high-voltage silicon rectifiers. He's responsible for new product definition and introduction, and he is a member of the wide bandgap cross-functional team. Now let me turn things over to our presenter. John, the floor is yours.
Hi, good afternoon, everybody. Thanks, Chris, for the introduction. Let's see if I can scroll down my screen. And okay. So the agenda for today is to talk about why SiC products help with solar inverters. So first of all, we talk about solar farms. What is a solar farm? What are the main requirements for the solar farms? Then a little bit about the inductors. We'll pick on the inductors as something we want to improve on and reduce for solar farms. And then go through the different pieces of the solar inverter. So as we'll see, there's two different string voltages. So how do we improve the boost circuit performance for 1100 volt string voltage with SiC? The topologies for 1500 volt string voltage and how SiC helps in some of these areas. Then there's the DC AC output stages, how SiC can help that. Then we talk about how we ensure high quality and reliability of our SiC products by testing them. It's not exactly the same as silicon, so we have to do extra tests for that. Finally, we talk about high accuracy simulation of SiC topologies. Then we come to the conclusion, what we find out about SiC. Just turn my watch off so I don't have a clock. So first step is to talk about what does a solar farm look like. So a solar farm is a solar power station, and the solar panels are arranged, it's drawing in 4 strings to keep it simple. In reality, you're going to have 9 to 12 strings are usually in a farm. So, and depending on how big your farm is, how big your area is, you have more or less solar panels. And then you connect the solar panels in this case, 4 different strings. And in this case, to a central inverter. This is what I'm showing you, is how it's connected to a central inverter. Now, these central inverters come in pretty standard but large sizes. So you've got 2.5 megawatts or MVA. You maybe have 5 MVA. You don't have a sort of ones in between. So they're pretty large. They have their place, but they're a bit difficult to maintain. You need a specialist to maintain them for the company who brings them in. So it's, you know, you'll see there's an alternative approach, which is being brought in and becoming more popular. It depends. There's some cases where central inverters are good. It's a quite complex topic, of course. So one thing I want to point out is the voltage on the strings. You know, the voltage on these strings, you know, when you add up all these solar panels, can get up to quite a high voltage. And you can say, well, I want to make the maximum voltage here 1100 volts. That's a kind of standard in the past for such solar inverters. And then for a certain power, you have quite a high current. So if you increase that voltage, which you allow on the central, on the string input here, to 1500 volts, you can reduce the cost of these wires. These are just blue lines on PowerPoint, but in reality, these are expensive cables, and reducing the cross-section of this cabling on all these solar panels here that's going to massively reduce the cost of your system. So this is why people are moving away from 1100 volt strings to 1500 volt strings. Again, it's quite a complex topic. So as you see both 1100 volt strings used, 1500 volt strings used. And then, of course, there's a connection to the AC grid. So that's the solar farm using a centralized inverter. What we see now is there's another trend to use decentralized inverters. So instead of having one large 2.5 megawatt inverter, you have, in this case, you're going to end up with 12 225 kVA inverters. This is quite standard size at the moment. So the decentralized inverters, obviously you have to connect them together. That's a cost which you don't have when you have one of these. Okay, it's connected internally. It's more flexible installation, right? If you just want to have, 2.9 MVA, you just add 2 more of these inverters and you're done. So you can adapt the size of your solar farm more easily with smaller blocks. You're going to have these output connections. That's a cost factor. And the trend in development of these is to get one of these inverters with increased powers, but not increase the size or weight of them. I forgot one important point here is that for maintenance, these inverters can be picked up by 2 people typically. So, it's a bit heavy for one person to pick up, but 2 people can pick it up. And if one of them fails, you pull them out, replace it, put it back in. It's a little bit easier to do that. You do the repair off-site. You can have spare inverters ready just in case there's a failure. Or it's much easier getting a replacement than it is when you've got a failed centralized inverter. So the maintenance costs are less. And maintenance is quite a significant cost of the inverters now that obviously the electronics cost is coming down. So the cost of the inverters is coming down. So that means the relative cost of the maintenance goes up. So let's have a look as an engineer. What affects the weight and the size? So I would say you've got 3 things which are heavy: the boost inductors, output inductors, and the heat sink. So the boost inductors, what determines the size of a boost inductor is the current of the going through the boost inductor, the inductance value itself, and the switching frequency. The output inductance is exactly the same. You can influence a little bit by topology as well. By using 3-level topology, you can reduce the size of the input inductors. Similarly here, I missed that point there. And then for a heatsink, the heatsink has to get rid of the heat, and the less heat you have to get rid of, the better. So you need to have lower switching losses and lower conduction losses. So, and indirectly, higher switching frequency will increase the switching losses. So you've got to consider that in the overall thing. So that's the basic concept of a solar farm with its centralized and decentralized inverters. And the idea is to get the decentralized inverters lighter. And in this case, for example, if you went up to 300 kVA, you could use 9 instead of 12, and that will obviously save you cost. So let's have a look. What affects the inductor size and the power rating of the inductor and the core power loss? I don't want to get into the winding losses. That's quite a complex topic, actually. I would say reducing the inductance will certainly reduce the cost because you reduce the number of windings quite significantly. So the physical size of the inductor, I'm picking the core, right? Is if you calculate it from the basic definitions of inductance, you will get a formula which is like this. It's unrelated, it's a different formula from the power formula, which also comes to the same conclusion, but you would also get this, is the size is, by reducing the current and by reducing the inductance, you will reduce the size. Okay, so if you reduce the inductance in a normal CCM inverter, you'd actually put your maximum peak current up quite dramatically. So these are obviously a little bit interlinked in reality. Power transfer is half Li squared peak in a flyback or boost type of configuration multiplied by the switching frequency. So if you increase your switching frequency of your inductor, you will increase the ability to transfer power. If you increase the inductance, you will also increase the ability to transfer power, but you make it bigger. And then finally, the inductor core power loss is, you can argue exactly what the coefficient, the exponent is here. It's, maybe proportional to the frequency, proportional to the square of the frequency, depends a lot on the details here. But by having a higher switching frequency, you're going to put up your inductor core loss, other things equal here. So increasing switching frequency give you higher power, but you've got to watch out for your core loss. Here I'm showing what it's often used in the market is powder core. These are quite big, and you can see from the iPhone here, the size of this. It's 600 microhenry, 30 amps RMS inductor. So then what we want to do is compare what happens if you move from 16 kilohertz to 80 kilohertz. So here are two inductors you rated at 30 amps. I didn't put it on here for 16 kilohertz, 600 microhenries here, and a 80 kilohertz inductor, 150 microhenries. It's a powder core. It's got lower weight. So if you go from 16 kilohertz to 80 kilohertz, that's a factor of 5 times the switching frequency. So you can keep the same power with 20% of the inductance. Here we chose to use 25% of the inductance. Obviously, there's other factors involved there. The weight of this is obviously lower. You can see pretty clearly it's 40% lower weight. And the inductor core power losses are roughly speaking 3 times higher, because although the switching frequency is higher, but the size of the core is lower. So you're going to get higher core losses. And the other point is here is this is quite a complicated discussion, is what is the copper loss, right? The copper loss, obviously here, other things equal, is going to be lower because you've got fewer windings. But then there's also the effect of skin effect and proximity effect on real inductors here. So you have to consider those points. I'd argue that these ones have probably got quite a high AC resistance. So this is probably biased to low core losses, high AC resistance. If you're looking at this from a formal power supply, you'd be using Litz wires and ferrite cores to get on there. But that's using standard power supplies. So I understand that these are type of inductors used today in most solar inverters sold on the market. These kind of approach, but the things are changing there, of course. Then we have interleaving. Interleaving is where you split the circuit into 2 pieces. So instead of having one 150 microhenry inductor, you use 2 75 microhenry inductors. This is used, for example, on the laptop I'm using. Interleaving is used on the power supplies. There's probably, I can't remember what it is now, 6 interleaved inductors for each VRM stage. That's what it used to be. Maybe it's changed since then. The idea is you get the much better power density by doing that. This is not so much used in the higher power levels, I think, because the inductors are so large, but interleaving is certainly used in 30 to 50 kilowatts. And again, you can see that the core weight is lower and the core power loss is lower. And as we said, if the inductance is lower, you have much fewer windings. And if you do things right, you should have lower copper losses as well. So that's interleaving. And if you look at an example of an interleave boost circuit here, you will reduce the ripple currents, you reduce the inductor size. If you do true interleaving, where this one is switched on 180 degrees out of phase with this one, your controllers go a little bit more complicated, but most people can cope with that. The EMI is also going to be lower. but you've got a you've got a good approach. And then if you increase the switching frequency, you can of course further reduce the size of the inductors. So it's going to take some time before the solar panels get down to the size of PC power supplies, but interleaving is certainly happening on the smaller ones. There's also the additional benefit of lower capacitor ripple current. If you do that, that's increases the lifetime of some of the film capacitors used. Let's have a look at the just some comparisons to do. So how can you do that boost? So this topology is set up for interleave boost or 2 strings. People use both, I would say. So you can have an IGBT and a silicon diode and a bypass bypass diode. The bypass diode is there to, well, one reason for it is to stop this inductor going over current when the string is initially connected. There's also when this voltage is very close to the input, you just stop turning this, and then you can have power coming through here. So these are the bypass diodes. So you have the IGBT and SiC diodes, SiC MOSFET, SiC diodes. My responsibility is to cover modules, and I'll be using modules and examples extensively through this presentation. For lower powers, definitely SiC is the right approach to use. So a SiC diode here, a TO247 4-lead SiC MOSFET is good for this application. And also we're seeing the use of our D2 pack 7-lead device. So people are not so worried about the creepage problems on this. It looks like you shouldn't be able to do it, but there's no problems with this. 7-lead D2 pack or Power 88 for super junction MOSFETs has been quite standard now. People know how to deal with that. And so for lower powers, maybe up to 30 kilowatts, people are using discrete solutions here. So my examples here are equally valid for our discrete portfolio. So let's have a look, see what happens. Just let's have a look at some proof. So let's first of all look at the DC curves of the devices. So here we have a 40 milliohm MOSFET. Here we have a 20 milliohm MOSFET, SiC MOSFET, and here we have 50 amp IGBT. So one thing to point out is the well-known effect is that if you start off at a given current, what voltage do you end up with, right? So you start a low current and you hit the yellow line first. That means that the losses of the 40 milliohm MOSFET, certainly in this range, are lower from a DC point of view. And it's obviously the, when you have 20, sorry, I'm getting mixed up the 40, but if you have an 80 milliohm MOSFET, so 20 volt, this is 80, you have much higher losses. You get a much higher voltage for a given current. Above a certain point, that's a well-known effect with IGBTs, you get better losses, but normally you're operating out a little bit outside that range. And you also have to consider the effect of switching. We're going to give you calculated examples in real applications in a minute, so we can do a fair comparison. So conclusion, SiC MOSFETs have lower RDS on in the have lower losses in this area. Interesting enough, they have a higher dynamic RDS on, as you can see here. This has got a very good dynamic RDS on, right? Dynamic RCE, right? To be extremely precise. But the point is, with an IGBT, you've always got this 1 volt drop, which is called by the bipolar effect, which gives you disadvantages. The boost diodes, I think it's pretty clear that if you have a 14 milliohm diode, it's the, what's it, that, okay, this is the diode which goes to the 40 milliohm device, which is this is the 40 amp SiC and the 20 amp SiC device. That's a typo. So obviously it's clear that the 40 amp SiC diode is better than the 20 amp SiC diode. AC curves, I think, is, we were talking about the benefit of IGBTs at high currents, but the E-on losses are significantly higher. And this is EON you've got to measure when you're switching against a certain device. EON without a defined device or defined inductance really doesn't make sense. Same with ERR. So ERR is defined as you are switching with this device against this diode under certain operating conditions. You know, you get totally different results otherwise. So this is when you're switching with the count. This is when they're switching with their counterpart. So this is when it's with the 15. This is with a 20 amp SiC diode. This is when you're with, again, with the 20 amp and the 40 amp SiC diodes here. So the losses are the EON losses are much lower because of the SiC MOSFET, lower intrinsic switching on losses, right? Then the EOF is, you've got tail current in an IGBT. You don't have that in a SiC MOSFET, so you see that very clearly here. And then the ERR of the diode. So here is interesting. The diode gets hit more when it's switching a SiC diode than it is with a SiC MOSFET than it is with an IGBT. So this is the IGBT, and this is because this is measured under different switching speed conditions, which also accounts for the differences here, because these are probably switching much faster in these examples. So if you look at the comparisons, we look at a fixed switching frequency to start with. If you look at a fixed switching frequency, you will see that the 40 amp IGBT, which I deleted from the last slide, is getting very hot. At 20 kilohertz, that's quite fast, right? So then you've got a 50 amp IGBT is getting up to, you've got a power level of up to 12.5 kilowatts, right? But this one is doing, this 40 milliohm SiC, this one's doing fine at 15 kilowatts power. And you see the power losses are the same. This is the 40 amp IGBT, 50 amp IGBT, 18 milliohm SiC, and 14 milliohm SiC. So you can see you get a much better efficiency and much lower, it goes together with the lower temperatures. And then with SiC, it depends exactly on the technology you're using, but if you have a lower temperature, you also get better efficiency. So that's a virtuous circle which you get when you're using SiC MOSFETs. Then let's have a look at a 10 kilowatt application and then see what happens when you switch the frequency. So, you really 10 kilowatt is kind of the limit for this 40 amp IGBT. Then we can, this 10 kilowatt here is no problem with the 50 amp. You can go up to switching frequency of 130, starting to hit the limit. You're getting very high power losses though. This is a green line here. Again, obviously the 40 milliohm SiC is much lower losses. And here you've got smaller diodes. So the switching frequency, you can see interestingly here, the power loss drops because of the smaller diodes, right? So that's what's happening here. But you can see the temperatures going up pretty high to achieve that. So this is what you see here. So in conclusion, we can show that SiC can go a lot quicker. SiC is at the moment clearly more expensive than IGBTs, but with the steps we're taking and the other suppliers in the market are taking, SiC prices are dropping down every year. SiC yields are going up. SiC quality is already there. So we see there. This is why we see the trend moving from IGBTs, SiC hybrids to full SiC. I didn't even show the IGBT plus silicon diodes, which you used about 3 or 4 years ago. The efficiency is just not there. It's not worth using IGBT plus SiC diodes for this power level. Higher power levels for sure makes a difference. So just to summarize, is that boost silicon circuits with full silicon are rarely used, and we use the SiC hybrid for the lower power levels and to get the best performance full SiC circuits to do that. I've just talked about that. I don't need to read that. So let's have a look at 1500 volts input. So far, we're looking at 1100 volts inputs. We didn't talk about the switch rating, but for 1100 volt input, obviously you need 1200 volt switches. For 1500 volts, you can't use 1200 volt switches. So there's two techniques which are used to do that. One is a symmetric boost, one is a flying capacitor boost. So if you look on the market today, you see symmetric boost circuit is being used, with flying capacitor becoming more and more popular, and we can see the reasons for that. So the symmetric boost topology is, just like to derive it for you, is this is a standard boost topology. If you do a kind of mirror image, stand on your head and draw it, what would it be like if you did a ground and the other DC input? This is what you get. This is just the same thing in reverse. I've just drawn it as two boost circuits and then joined it together to make a classical symmetric boost. So it works in exactly the same way as a normal boost. But one point here is you see the ground here is connected through. So I just want to highlight that later week, but just make a point here. You couldn't really connect the grounds of all the strings at this point. So let's have a look at what we do. We have a product for 3-level boost, 1500 volt system, and we use 10 amp SiC diodes in parallel, right? So we have 18. So there's obviously 6 stages here. So there's 3 of these in parallel used in that, and that's has a good effect on slightly reducing the RTH, and it's a common technique we use. So if we look at this, the benefits of using the SiC is not necessarily on the SiC, if you remember. Using the SiC reduces I didn't actually show the comparison actually, but using the SiC reduces the temperature of the IGBT. So, and it depends a lot on your switching frequency. Here, if you're running at under these operating conditions, then it makes a lot of sense. But it really does depend on your conditions, right? So sometimes an IGBT is better, sometimes SiC is better. Again, really depending on your topologies and where you are. So, but this has been popular use in decentralized solar inverter customers who are using this as we speak today. So the symmetric boost, I didn't say the voltage, I missed that point. What we use here is a 1000 volt IGBT and 1000 volt SiC, 1000 volt IGBTs, and for silicon we use 1000 volt diodes, and for SiC we use 1200 volt SiC diodes. And we have extremely good 1000 volt IGBTs. We've spent a lot of effort making sure we optimize that, especially for this 1500 volt market. You can have full SiC circuits there. I would say if you look at the cost benefit for full SiC, it's not quite there yet. They're being considered, but it's for different reasons. It doesn't make sense in all applications to do that. Your inductor is going to be quite expensive to do that. So, but if you look at the trends in the industry, it's moving towards that. People are asking us to make things like that. And yes, in the future, you're going to see that trend from silicon, hybrid to SiC. I think at the moment, in most cases, you'll see the conclusion is we're doing a lot with SiC hybrids, and SiC is coming through. Then there's a flying capacitor boost. This is a technology webinar as well, so I'd like to put a little bit of a kind of technical training on this. So it's not clear to everybody how a flying capacitor boost works. I would say, okay, for me, it's like a voltage doubler and a boost mixed together, right? So just for this discussion, let's mentally short circuit the boost inductor so we don't have to worry about the voltage drop across it with a DIDT, right? Just make it a wire. So if we do a voltage doubler with this, we say, oh, okay, nothing's charged, so we better charge up this capacitor. So how do we do that? So we come out here, come around here, turn on T2. So we turn on T2, keep T1 turned off. So go, this gets charged up to the input voltage because I'm ignoring the boost. But this is a straight wire, so it's the input voltage. So this is now charged up to V in. So now what I want to do is I want to sort of bootstrap this up by connecting this switch and then bootstrapping this up so that this voltage is then V in, and then this voltage is also V in, and it's boosted up to twice V in. So this is how a voltage, this is a standard voltage doubler. Everybody knows how that works. It's this is how it works. You won't be surprised to see that these two switching configurations are used in the actual flying capacitor. Now, if you work this out, you will see that you can also do a boost. So let's do a boost in a simple way. I turn on T1 and T2, then it will boost up. I let the boost inductor free, turn off T1 and T2. It will act like a normal boost circuit. The point of doing this as well is to, this half voltage across here reduces the need for using 1500 volts in. So this could be 1500 volts, but this is then half of 1500 volts. So let's have a look at how the topology works. So you've just seen that because I explained it, and you just saw that, I explained it. And you saw this approach. I just explained this is a freewheel cycle here. And there's two operating modes. I haven't found a good paper in the literature. So I found two papers, one describing it duty cycle less than half, one with less than half. And you can see one of the benefits here is that the inductor current has at twice the ripple frequency of the switching of each T1 or T2. So it's basically a switch at double the switching frequency. So if you say, depends, what do you call the switching frequency? If you call this the switching frequency, right, then this is double. So if you double the switching frequency for the same power, you make the inductor size smaller. Also, if you're very observant, you'll see that there's only one inductor here, whereas in the symmetric boost, there are two inductors. So this saves the number of inductors and also doubles the switching frequency. And then we have operating modes of D is greater than 5. You go and look at this afterwards. I would work this stuff out. The ripple formulas are a bit different, and you be careful when you're defining what the duty cycle is, because some papers use a different duty cycle definition from others, so you get a factors of 2 in here. But basically, it's similar to a normal boost. Do that. So this is a flying capacitor boost. So what's so good about this is, okay, only one inductor needed, and it switches at twice the frequency. Whereas here, here you have to have, you'd split the inductor into two pieces, right? So, okay, you have two smaller inductors, right? But here you will have one inductor, but twice the switching frequency, and that works out better. There's a shared ground. I'll show you that on the next slide. I think it's quite easy, but remember here you've got you can, if you have two strings in parallel, you can connect them together. And if you have two symmetric boosts in parallel, you have to have separate return wires for the string. I don't know if you need to do that. I'm not an expert on that anyway, but I understand that in some configurations, you can have just one ground wire. That simplifies the connectors and wires. And because of that, all this stuff, the EMI inductors, Y capacitors, and potential induced degradation circuit. That's something I learned about recently. Our colleague who's an expert on this was commenting that this is actually much simpler when you use the when you use the flying capacitor boost. Disadvantages is there's extra circuits on here because you need the flying capacitor, and you need to worry about the startup circuit. I don't want to comment further on that. There's a lot of discussion on that. It's out of the scope of this presentation. That's something you need to look at if you ever use that topology. And I've repeated this slide. I just want to point out the benefit of the reduced wiring. Right here, the ground wires, right, you've got 4 different ones. Whereas if you're using a flying capacitor boost, I understand that you can connect them all together. I'm not sure if that's easy to do or you can do that, but that is a possibility. And if that's a possibility, you certainly reduce the complexity of the installation by doing that. So in conclusion, SiC diodes are good in the fly cap boost topology. Is still depends on your switching frequency, but if you run at a high switching frequency and you're careful with your design, it's actually quite tricky to do that. You can use SiC. The power dissipation at 300 kVA is quite high, so you've got to be a little bit careful. So SiC will help you there in the flight gap boost, and certainly on the symmetric boost, SiC diodes are essential. Last but not least, we want to look at the output stages. The output stages, depending on your topology and power, is T-type MPC, I-type MPC, or AMPC. Let's have a look at a pass we've in our product portfolio, which we're using for 1500 volt systems. Here we're comparing the effects of silicon nitride and aluminium oxide with SiC diodes, to show that's also possible. This is a aluminium oxide solution. We're running here at 73 kVA, and we're getting up to, we can run up to 73 kVA with our maximum junction temperature of the transistor, right? So you get better power here. And then on the 255 kilowatt, by changing the silicon nitride, you reduce the R theta JCs. You can compare it later if you look at the slides. And then you have the 85 kVA at the same temperature. So you get in the same package more power density by using SiC to start with, and then using an additional silicon nitride interface to do that. We don't, for various reasons of our manufacturing process, we prefer using silicon nitride to aluminium nitride. So, but this is a very robust, very good performance. So again, these are the devices, and these are for inverters which already go up to 255 kilowatts. For sure, we have parts in development and in discussion with our customers going well beyond this. This is a public webinar, so I'm clearly only talking about the stuff we released and can openly talk about today. But we are moving forward to make these values higher on both the boost and the output stages. Finally, T-type MPC. This is used for I don't know, 80 kilowatts, something like that. So we have by changing the silicon diodes with SiC diodes, we can get much more power. So this 80 kVA application, and you see with the 160 amp version using silicon diodes and 200 amp using SiC diodes, you get for relatively minor change in the cost, you get a big improvement in performance. And moving forward, using SiC MOSFETs here is certainly a possibility, and clearly it's more expensive, but sooner or later, I think the benefits will be there, so people will be using it even for lower power applications with SiC MOSFETs as the cost comes down. So in conclusion, today I-type MPC and AMPCs with IGBTs with some SiC diodes are used today. You get a much better power density with SiC hybrid on the output stage, so it helps you do that. And you get higher power density by using SiC diodes. I want to briefly talk about then, how we check our SiC products. I think this is very important. This is from some information we shared in public several times, and I'd like to do that again. So the challenges with SiC is the defects, right? Is the first thing is you get defects in the SiC crystal structure. This is something to do with the fact that you don't have this is not 90 degrees in the SiC crystal structure. This is slightly shifted. You can probably see a little bit here. You slightly shifted, and this means that cracks will propagate, and they're very difficult to detect. So this, if you made a chip with it, it would work properly, and then after a while it would fail. So, and then there's other things like the difference between the silicon, so with the SiC and the silicon dioxide, the gate oxide. It's not a native oxide. It's not actually grown on there. So there's a difficult so it's actually a difficult interface to manufacture. This is the same for all competitors. Right? It's not no different for us or them, right? It's always the same. So you've got to be able to deal with this. So what we do is we monitor our substrates very carefully, and with SiC is actually transparent, so you can actually see through it. And when you've got metallization on it, of course you can't, but when you're doing the growth, you can see through it. So you scan it, you scan after epi again, so you make sure you've got a good substrate to start with. Grow layer, which is used for this is used to support your breakdown voltage, basically. This is a post-epi scan. And then you do the in-process scanning. And then we do the burn-in. We talk about burn-in, electrical test, and inspection, right? And this is why we are one of the first guys to do AEC-Q 101. So this is automotive qualified. We were the first to launch with AEC products, automotive, because of this thing. So you can't just ignore these defects. You've got to get rid of them. So if you look at the classical papers on oxide integrity, you have the intrinsic oxide integrity, which is, you've got the oxide and you assume that it's perfect, right? What will happen over time? How will it break down? And you can run our devices at high gate voltages for short times. The long-term reliability would go down. But in principle, that's possible. So, but we have to do that for lifetime testing of that. We also have there's defects, and there's a number of different defects which you get on SiC, which you can't get rid of apart from by burn-in testing. So we do a burn-in testing. So you can put your discrete components in a burn-in oven, or you can do wafer level burn-in, for example. So you burn in the devices. So you give specific stresses, which is briefly mentioned here, right? Determined by lifetime requirements, and a certain temperature and a certain gate voltage is put on there. What it is depends very much on which device we're using, but we can very much, we screen these devices, all our devices, put them through burn-in. And we get failures, a little bit of failures, right? It's not much, but we don't want to ship those to customers, right? So it's very important that we do this burn-in. And this, again, this is to do with the gate oxide. Different companies, I guess, have to solve the problems in different ways. But the idea is you've got to get rid of stuff like this. You can just, you can hope that you never get dirt in it, right? But, we want to be sure. So we're guaranteeing really high reliability of our product. So that's about the burn-in process. The other thing is for simulation models. On Semiconductor has been very active on physical models, and there's been a lot of development on IGBTs. And the same thing is we have physical scalable models for silicon carbide. So the scalability is maybe less interest for a customer. Okay, we can scale it and I can make a die size what I want to, right? But for a given die size, you can get accurate modeling of the effects. For example, how the diode works, the capacitances of the diodes. What it is in simple terms, it doesn't use a SPICE model as a standard library. It uses basically a set of equations, and we match those equations to, or the parameters of those equations to what we actually do, right? So it's not just, okay, we think of a few nice equations, stick it in. We using special techniques described in this paper. At one operating point, you use a reverse matrix operation to define the different parameters based on the observable parameters you have. So it's quite a complicated principle, but we can also do process variations on this. So that's also important, especially in the automotive world, where you want to say, okay, you say your gate oxide is this. What happens if it varies a lot? What about your process parameters? We don't do that. We do that again indirectly from the models. We take the worst case parts and then we feed them back in and make these models so you can actually determine the reliability very easily. The other thing is that these are electrothermal models. This is a simple circuit I've done. Normally you put a Cower network on here, so I just put in an RTH just so you can see it more easily. What happens is here you set your temperature in SPICE, let's say to 80 degrees, right? The RDS on then will automatically adjust to the temperature of the actual junction, right? So let's say you do a short circuit, right? Or then there would be current will be very high. The RDS on would then increase because you've got a higher temperature, and it would model that very accurately. If there was no current going through it, obviously, then the temperature of the die would also be then 80 degrees C, and you wouldn't have the effect. So this is, the self-heating effects are included, clearly reverse recovery, and also the parasitics. I didn't want to confuse everybody. I didn't want to put parasitics in here, but you basically put a parasitic in here or here to model the module and circuit levels. And these are also for discretes. For example, for our discrete components, we have excellent models which correlate to actual data. So this is the important point. So you can be sure that if you use our models, they line up pretty well. That's good. So that brings me to the conclusion here. So what do we talk about? The design challenges are to get improved power from a certain size of inverter. So these modular inverters, we want to get more power out of them so that two people can lift them and replace them more easily. And how do you do that? You need increased switching frequency, using different topologies, and obviously using improved efficiency, which you can get in a number of ways. So where we are on SiC boost stages, I would say we're pretty much on the transition to full SiC MOSFET solutions plus IGBTs. Symmetric boost stages, definitely SiC diodes using symmetric boost. Moving towards full SiC at the moment, it looks expensive, but I think there's big advantages in full SiC approaches here. Also, there's you've got half bridges you can use as synchronous boost and whatever. So a standard half bridge portfolio, which we're coming up with, will actually be very useful there. LICAP, SiC diodes, they're SiC MOSFETs. I think we've done some calculation on that. It looks a bit expensive for that at the moment, but again, when costs come down, maybe that's better. AMPC, TMPC, IGBTs and SiC diodes is what is used for the higher power levels today. And I see, the trends, every switch which is an IGBT, step by step, you're going to start replacing it with a SiC MOSFET. SiC MOSFETs are more expensive. SiC diodes, you can't replace all SiC diodes with, all silicon diodes with SiC diodes because the forward voltage of a SiC diode is a bit high. So in some cases, that's not a smart move. But when you're doing that with changing a SiC MOSFET, then I think changing IGBT into a SiC MOSFET makes a lot of sense. We talk about strong controls like burn-in, monitoring, control of our own supply chain, and that ensures good outgoing quality and reliability. And we have the great design tools to help you out on your next module design, SiC hybrid, full SiC MOSFET, discrete MOSFET design. We have all the models for that. So we have the tools to support you there. So I've come to my 15 minutes. So I think we have 10 minutes for any questions. So I hand back to Chris then, please.
Thank you very much, John, for this excellent presentation. So during the presentation, we received a number of questions. If you would still like to submit any other questions, please open the Q&A window on the right of your screen and send your questions to all panelists. So John, first question for you. What do you think about using 1700 volt boost converters instead of fly cap boost?
So let's go to the drawing to compare the two. There we are, here we are. So this is a, let's just use that, the 1700 volt boost stage would use a 1700 volt device here and a diode here. I see that as a interesting development. You would have the benefit of a, here, you have a benefit of the common ground like you do with the fly cap. We would see good performance. We're starting to evaluate that, to be quite honest, right? We have in our development plans, we are thinking of doing, we're developing 1700 volt MOSFETs to go with our diodes. We have 1700 volt diodes here. So the question is, you know, what is the benefit? We see the benefit as a simpler solution. You go back to the one inductor, you go back to a different switching frequency, and the idea is what voltage. You haven't got this stacked approach, so the idea is what voltage we need to do that. It's the trade-off between the actual rated voltage you need. It's, you know, 1700 volts is what's the actual breakdown voltage, right? So maybe it's 2100, 2200. It's that optimization which is important. So I see that as an important trend. Certainly 1700 volts or that class of SiC MOSFET is very important in future, not only for solar inverters, but also for EV chargers. And if there's a bigger market for the 1700 volts, I see that this would make things a lot better. So yes, I think it's an area which we are actively looking at. That's what I like to say there. Thank you. Thanks for good. That's a good question.
Okay, thank you, John. Next question. Do you offer step files and thermal models for your modules?
Yes, we do. Then normally at the moment made on demand, but we're getting to a position where we can more automate that. So yes, we do. We offer the models for the devices. Normally at discrete level, that's what we do at the moment, because getting the inductances right is a bit tricky. You can get them exactly right, but then the models are too complex. So that's an area we're looking at. But discrete, so what we do for simulation is, worst case, we use discrete components, and we certainly offer step files to the customers we're working with. At the moment, we don't have that available as generally on our website, but you know, we are getting there. So we have them. We don't have them for the devices available on the web, but we have all the discrete models on our website for simulating certainly these SiC devices, SiC hybrid modules.
Okay, thank you, John. Next question: where do you produce your SiC MOSFETs?
Our SiC MOSFETs are produced in Bucheon in Korea, as are our SiC diodes. We also, I'd like to point out, we are working on making our own SiC substrates. That's also public information. We already make our own silicon substrates. Maybe people don't know that. We have a factory in Rožnov in Czech Republic, where in the old days they poured in sand in one end and had computers coming out the other end. That was the business model of the Czechoslovakia at the time. So we, on Semiconductor, took on the silicon wafer manufacturing. So we make our own wafers. We have a mixed model. We buy wafers from outside. We make our own. It's a supply topic. So we make our own SiC wafers. We have an announcement we made with a company, GTAT, where they supply us some of the material to do that. And so we also make our SiC substrates. Finally, an important thing is the epitaxial growth. We have our own epitaxial growth in places, and one of them is in Bucheon, Korea. So again, we have the full flow. And all our modules, all our assembly is done internally. So we have a full internal flow from SiC. That's
Okay, thank you, John. And then one last question for you. Does bigger SiC wafer inch mean higher probability to have substrate defect?
Yes, it's clearly a challenge. Higher wafer size causes problems because you've got bigger wafers and more chance of a defect. But you know, those over time, those problems will be solved. And like any other wafers, you know, things will move from 6-inch to 8-inch to 12-inch. You know, 12-inch SiC at the moment, maybe it's right, but you know, one of these days, companies will be getting there. So yes, it's a challenge, just like it was when moving from 6-inch to 8-inch in the first place, or from 8-inch to 12-inch in the first place for silicon. Yes, it makes a lot of sense to do that, but you've got to work out how you reduce your defect rates on your larger wafers and things like that. So it's a but it's clearly, if you look at a long term, you know, it's going to happen. We as on Semiconductor, one of the first, we weren't the first in the market with SiC diodes, for example, but we moved in. We were one of the first with 6-inch wafers. So we started immediately with 6-inch wafers. We didn't go for the 4-inch, 5-inch, 6-inch conversion. So 8-inch is the next step, and then it's clear that's the way things are going. How quickly? How fast, we don't know. It's not released yet, or anything like that. But many companies are looking at that. That's quite normal. Also, you have to think of the supply of 8-inch wafers as well. Right? It's not just doing the processing with 8-inch wafers. You know, you have to do the making sure you can buy external 8-inch wafers as well. It's quite a complex topic. That's a good question.
Thank you, John. So these are all the questions for today. So on behalf of On Semiconductor, I would like to thank everyone for attending, and I wish you a nice rest of your day. Thank you.
Thanks very much, guys. Thank you.